All right. We are going to finally start our main course contents for today's lecture. The first topic we are going to cover is actually we are going to solve IVPs. Okay. And the first method we are going to use is Euler method. Those who already completed differential equations 1 are already familiar with this method a little bit. And if you already took numerical methods, then you are very much familiar with this method, but still I'm going to give a small briefings at the beginning. This is how Euler method actually works. Say we have an IVP that looks like this, dy by dx equals to f of some function of x, some function of x and y. This is a differential equation, and if we are given an initial value, for example, y at x naught is y naught, then it becomes an initial value problem. So the main idea is, since this differential equation is of order 1, the general solution will contain one unknown parameter or one arbitrary constant. But once you decide an initial value, that is, you decide a point x naught comma y naught through which our curve will pass, it means physically what it means for the differential equation. Say the general solution looks like this, something like y equals to some c into some g of x or something, anything that contains an unknown parameter, then it will indicate a family of curves. For different values of c, we will get different curves. But once you decide that our point will pass through x naught comma y naught, say for example, this is x naught comma y naught, then all the remaining curves, the only curve that satisfies this condition is this one that I'm drawing with pink color, right? And no other curve will satisfy the initial condition or will not pass through the given point. So this particular curve becomes the solution of the IVP. Now, say for example, we are given this IVP, which means at least we know one point x naught comma y naught, one point say x naught comma y naught, to which our final solution curve will pass. Say this is the final solution. Now, if there is a method already, there is already an existing method to find the analytical solution, then we will not actually need the numerical methods, right? We are going to need numerical method in situations where we cannot find the analytical solution. So technically, even though this is the solution curve, think of a situation where we actually do not have any method to find the actual curve. So what we do is try to manage some points, in most cases in regular intervals, on the curve, so that we can at least find a set of points. For example, say this is x naught and the next point is x1. There is no problem in getting these xi's, because these are just x points selected by us, right? Let's finally, the last point is, say for example, xn. So the first column is decided by us. We choose some values of x in the interval x naught to xn. Say this x naught is a and this xn is b. Then we are trying to find a set of two-dimensional points for this particular situation, a set of two-dimensional points that belong, I should have written inclusive. So a set of points in the interval a comma b that satisfies, or that those satisfy or almost satisfy this curve, right? Almost satisfy this curve. So I don't know what I wrote here. Anyway, so technically we are trying to find uh, values y0, y1 up to yn, so that these points xi comma yi, for example, this point is xi comma okay, here is the thing. Let's denote the solution by caps, because say xi comma yi is the actual solution, the actual point on the curve. But using any numerical method such as the Euler method, we are actually trying to find another point xi comma yi cap, which lies very, very close to the actual solution. In the best case scenario, we are going to probably have the exact point, but in most cases, there will be some margin of errors. All right. So this is the situation of the problem. This is the task that we need to accomplish, right? We are given an initial value problem. The situation is like this. We cannot actually find the analytical solution or real solution. Instead of that, we are going to try and find a set of coordinate points that lies very close to the actual points on the curve. But how do we do that? Okay. At least there is one point we are sure that it is on the curve, and that point is x0 comma y0. Let me rewrite the IVP first. F of xy with the initial condition y at x0 is y0. So at x0, the value of y is y0 for sure. So this is the actual value. Now we are at x0, and this is our a, and this is probably b. The first thing we do is divide this entire interval into n segments. So this is x1, this is x2, and so on. So let's write clearly. So this point is x1, this point is x2. In most cases, we will choose equal intervals, equal subintervals. And finally, at the end, this point is actually xn. So there are n subintervals, but n plus 1 grid points, right? Because we started the index with 0. Now, say the original curve in this interval looks like this. But there is no way we can find that, of course. So here is how we manage the approximate values. We don't know the value of y at x1, but we have another tool. Actually, look closely at this expression. This equation actually represents the slope of the function at any point, right? The right-hand side is a function that will give us the slope of the function at some point xy. So why don't we find the slope at x0 comma y0? We can manage that, right? So this is the value of dy by dx at the point x0 comma y0. So using that slope, what we can do is manage a straight line, maybe the tangent equation of the tangent line. We can easily manage that. How? Because the equation, any equation of a straight line through x0 comma y0 should look like this. Y minus y0 equals to slope times x minus x0, and the slope is f of x0 y0. So if you make y the subject, you get y0 plus f of x0 comma y0 into x minus x0. Okay, now since we have chosen equal subintervals of equal length, so let's denote that length by h. So technically, if now we are trying to find y1, which should be this point, then to find y1, we should put x equals to x1, right? Now, if you put x equals to x1, then this becomes x1 minus x0. This is f of x0, y0 as before. And this is y0. And what we are getting is y1. Not actually y1, but the approximation y1 cap. So how to find the next value of y? The answer lies in this equation, and we can use this equation iteratively by like this. If you have yi, then just add f of xi yi. You can see that this value is just 8. So you can just add 8 times f of xi yi to get the approximation for yi plus 1. I'm using cap for the theoretical discussion. In the code, I will not use any notations like cap. I won't be able to anyway. Anyway, okay. So using this equation, what we can get is this point. So instead of managing the actual equation, we are approximating using this equation of tangent line. And we are putting x equals to x1 in that tangent line. And we are getting this point. You can see that clearly there is a difference between the actual value and the approximated value. And this value is nothing but the error. Since the point has index I equals to 1, the error for this point will be denoted by E1. For the points, that is, we are denoting yi minus yi cap by EI, the error. So now this result is not perfect. We have error. There is an error in the value, but you can understand that if we choose very small value of h, the error will become very, very negligible. And then we can iteratively use this method to manage y2 and y3, etc. That is, in the next, now we are actually considering that this is our next point, x1 comma y1 cap, not x1 comma y1. Now we are going to use the same technique again iteratively. So what we will get is, let me show you. So we know how to find the value of the slope at x1 comma y1. The slope is the slope of this tangent line, right? But we are not going to start from x1 comma y1, but rather we are going to start from x1 comma y1 cap. So we will move along this direction to get the approximate value of y2 cap. We are going to use this again and again, and finally at some point we will reach xn. So technically, most probably the points, the final values of yi caps would give us an impression that the final solution is something like this. The green line, the blue line, which is not, which is very close to the green line, but not exactly the green line. That is, using this method, we are going to manage some approximate values with some margin of errors, which we can, use for the time being. Okay, my audio is breaking. Is my audio clear now, or is it still breaking? Is my audio clear right now, or is it still breaking? Can someone tell me? Okay, I have asked actually 2 questions. I don't know which one have you answered to when you answered no. Is it still breaking?
So কথা ভেঙে ভেঙে আসছে।
Okay, it is still breaking. Has it been breaking from the beginning? Or it just started now?
Like 2 minutes ago.
Okay, about 2 minutes. Okay. Should I, if it's not breaking now, I can repeat. Okay. Am I audible now? Okay, I will speak a little slowly if that helps. Should I repeat some portion of the lecture? From where should I repeat? Or
I'm
are
not
you
clear
okay?
about how we're calculating the error.
Okay, you are not clear how we are calculating the error. Okay. Let's since some of you were not being able to hear me properly, let me repeat the main key idea very briefly. Say this is x naught, this is y naught. All right, this is y naught, this is x naught, and say, for example, our curve goes like this. What we are doing using this equation is the equation of the tangent line through x naught comma y naught. So let me draw the tangent line in red. So this is the equation of the tangent line. And for the sake of understanding the visual more clearly, let's write x1 here. So maybe x2 is somewhere here. I'm using wider intervals so that it looks more understandable, all right? So this is x naught, this is x1. So this value is actual value y1. But we are not trying to find the actual value. Rather, we will use this equation of tangent line. And finally, we will put x equals to x1 in the tangent line and get the value y1 cap, which is this value. This is the point on the tangent line where x is equal to actually x1. So this is y1 cap. The actual value on the curve is y1, but we are getting y1 cap. So there is this little bit of error e1. For the ith point, yi is the actual value, yi cap is the approximated value using our method called Euler method. So their difference is the error ei, which is going to be non-negative for every point, right? So this is how we are actually approximating y1 using the value y1 cap, and this is how we are getting the error e1. Is the method clear so far?
So the method is clear, but in the situation that there is no other way to calculate the actual point, how would we know the amount of error
Okay.
that was?
Oh, okay. I understand your question. Forget that for now. All right. Okay. Sometimes just for testing you guys, I will provide a problem for which you can find an actual solution so that you can compare the error of the method. Of course, when we develop a new method, we test that method using known situations, right? So in those known cases, we will have the value of the actual values in hand, right? Then we can find the error. But in problems where we actually don't know the real solution, we will not be able to calculate the error. Am I clear?
Audio is breaking again.
My audio is breaking again. Okay.
Yes.
Okay, but
Yeah, it's
but Ilham, did you get your message? Did you get your answer, or should I repeat it?
Yes, sir.
Okay. Now, what we are going to do is just briefly mentioning, because I was breaking back then, we are again going to find the value of the slope using the point x1, y1 cap, not y1, but it will be very close to the value of the slope of this tangent line at our point. What we will do is, starting from x1, y1 cap, we will move along this straight line and declare that this pink point is our value x2, y2 cap. Okay, this is a problem. Internet has been a big issue recently, especially from Thursday, right? I'm using my
sir. Should we try Google Meet?
Does Google Meet perform better? Okay, Google Meet.
Um,
If I use Google Meet, I will have another problem because at the moment, I do not have any recording device installed in my PC. Google Meet does not allow us to record in the non-pro version.
it's okay, sir. I can use OBS Studio to record.
Okay, since we are already very, I mean, I would like to continue using Zoom if the problem is not continuing anymore.
It's just that, sir, it goes away, but sometimes it comes back and it gets harder to understand.
I see, I see. Okay. We are done with the theoretical part, actually. I will move on to the coding part. I think things will be better. Let's try it 5 more minutes. All right. We will see. If the
Okay, sir.
problem still remains, we will move on to Google Meet then. Okay. So the first approximate point is y1 cap. The second one is this. So if we go like this, maybe finally we will get an impression that the solution curve maybe look like this, which is not the actual curve, but which is a very close approximation, considering that we can always choose small values of h. The smaller the value of h, you can understand that the smaller the error will be. So we are going to use this idea today to solve an initial value problem. I'm going to share the book by Barden on screen. Okay, I think most of you are familiar with this book. It's the book by Barden. Uh, uh, I'm writing the name of the writer in text message, sending to everyone, in case someone is not familiar with the book. In this book, I'm at page number, I think it's 267. 267, yes. And here is the algorithm for Euler's method. And there is a problem, this example 1, where, okay, so you are already, Fahim said that you are already using this book for numerical analysis too, all right? So there is a problem in this page where they gave an initial value problem, and they also provided the actual solution. And not only that, this actually solved the problem using Euler method. And finally, they found the solution and presented the solution in a table along with the error. Because they provided the actual solution, we can always find the error column, right? So since this problem is already solved, the code is not given, but the final table is given. So it will be easier for us to verify if our code works, right? So if we just solve this problem, since this is ready. So let's solve this problem using Euler method. I'm starting with this. It's taking me a bit longer than usual. Okay. Let's
Sir,
clear. Yeah.
it's still showing. Are you trying to show us a different screen?
I just ran the code blocks. The code blocks code block software should be visible to you at the moment. Is it?
It's not, sir. I think you're sharing just the window. You should probably change the window
Oh,
from Zoom.
okay. Thank you. It should be now.
Yes, we can see it now.
Okay. Thank you. So I created a new file. Let's save it somewhere. Let's name this file Euler. And let's start coding. All right. So let's call our program Euler as well, because why not? Okay. The first thing we will do is write implicit none. Doing this is a good practice because the control is now in our hand, right? So let's declare a real array called X. For now, say we define the dimension to be 100 and Y 100. So you can understand that we are going to, in the PDF, you can see that they use T, all right. So we are going to use T as well, just for being coherent, all right. So let's write the variable name T. So T and Y are already what you should know what these are, right? This Y and this T. Okay, now 0 is the initial point, and at that point, value of Y is 0.5. So for these two, let's write A equals to 0 because we are starting with 0. And even though this is an initial value problem, the solution should be in some window. So they actually solved the problem. Let's see. Okay, they are using the window 0 to 2 for T. All right, so the ending point should be 2. So let's write B equals to 2. To avoid floating point issue, I'm writing 2.0 and 0.0 instead. And let's write Y naught. Here, the symbol I used is not O, but 0. Y naught is 0.5. By Y naught, you can understand I meant Y at the value A, at the point A. Okay. Now, at some point, we are going to need to use this function, y minus t square plus 1. So let's call this function f. So we have to write the name of the function, declare the function here, and let's write the function here first because it will be shorter. Function f, it can take two arguments, t and y, right? So it's showing that we have 10 minutes left for the Zoom meeting. In case the meeting ends, please rejoin. Okay, I have to write implicit none here again because the variables are local here. Write real. We must include the name of the function f as the return variable. We must include the input variables t and y as well. And the return expression is, let's check again, y minus t square plus 1. So y minus t square plus 1. This is how a square or to the power is written in FORTRAN. Okay, I think I won't need anything else in the function. Okay, let's write another function already for the actual solution. We have the actual solution here, yt equals to t plus 1 whole square minus 0.5 e to the power t. Let's already write a function, say for example, the name is actual, so ACT, short for actual. It takes t as input. Let's write implicit none again, and real. The input is t, the output is ACT, and ACT is equals to, the expression is t plus 1 whole square t plus 1 whole square minus 0.5 times e to the power. There is a library function for e to the power in FORTRAN, which is exp t. I think this was the expression, right? Yes. Okay. Now let's get back to the main body, and I have to add the function ACT in the declaration as well. Okay. We are going to need a couple of loop variables probably. So integer, let's write 1 for now. Okay, now in our method, we actually used something called h. And depending on that subinterval length h, we would get the number of grid points. But here, for example, if I denote the number of grid points by not the number of grid points, but the number of subintervals n, so that the number of grid points is n plus 1. Okay, someone said we were going to need T naught, but T naught is A. I denoted the first value by A and the last value by 2 in the T axis. Okay, let's get back to the decision. Earlier discussion. Okay, say if the number of subintervals is n, the number of grid points is n plus 1. You can understand that because we are starting with x naught or t naught or y naught and ending with tn or yn. So there are n plus 1 points. So what we can do is we can write n equals to simply b minus a by h plus 1. We can always write that to find the final number of points. This plus 1 is, as I have explained earlier. If I do not write this plus 1, we will get the number of subintervals. The number of grid points is 1 more than that. But there is one problem. B and A, these values are floating point values, right? And after dividing by h, they will still produce a floating point value. But n is an integer. So even if b minus a by h, for example, if you choose h equals to, say, for example, 1. So b is 2, a is 0, b minus a is 2 minus 0 is 2, 2 by 1 is 1, 1 plus 1 is 2. We will get n equals to 2, but there will be a problem because maybe at the end we will see n equals to 2.0000001. IDEs do that, right? Compilers do that. So if we get that 0.0, that 1 after a string of zeros after the decimal points, it will be harmful for us because we are going to use loop and array at some point, and array index cannot be non-integer, right? So just to avoid that, what we are going to do is fix the value of n at the beginning, say for example 10, and instead of finding n using h, we will find h using n. So h is b minus a by n. Okay, so there are 10 intervals. So h is going to be 0.2. All right, so we have to include h here as well. All right, now let's create our T array first. So we are going to use loop for that. Do I equals to, starting from 1, ending at n plus 1, Ti equals to a plus I minus 1 into h. So this is the old formula for AP, right? So using this, we are going to start with I equals to 1. So T1 is just, since I equals to 1, I minus 1 is 0. So T1 is just A, the first value that we actually needed to start with. And at the end, when we will put I equals to n plus 1, then n plus 1 minus 1 is nh. A plus nh is, you can see that from here you can simplify that a plus nh is b. So this is exactly how the array should have been. Just experiment a bit to see if this actually worked well. So let's write this to see if the array was made. I don't know what. Okay, I have to use a do loop, right? Let's see now. So starting with 0, ending at 2, the interval is 0.2, and you can see that there are some minor fluctuations here. We should have 0.4, solid 0.4, but we have 0.400000006. So this is that non-zero value after a string of zeros we are talking about when we say that n could be converted into something and not exactly an integer. So this was the thing I was talking about. Anyway, so now let's move on to the actual part of our code. So basically, technically, the first value of y is already known, right? So let's add that here. The first value of y, which is y1, is simply y0, which is 0.5. This is known. What we are going to do is start from y2. Use Euler's Euler equation in Euler method to find y2 first, and then y3, then y4, etc. So here the loop variable should start from 2, or I can do this. Start from 1, end at n, just write yi plus 1 equals to, we are going to use this equation here. We are going to use this equation. Yi plus 1 is yi plus h times f. So yi plus 1 is yi plus h times f of xi comma yi. Should work. Let's see. Write yi beside ti. Let me compile and run. Okay. Oh, I've mistakenly wrote x because the main equation contained x, but here we have t, right? So okay, so we can see that the value of y is exactly 0.5 at 0, and it sort of increased with increasing values of t. Let's compare the results with the values given in Barden's book. Sorry. Okay, as we were saying, we have already a tabular, the solution in a tabular form in Barden's book, and this is the solution given in Barden book in tabular form, and in the black screen you can see my solutions. The numbers, okay, by w, my yi is wi in Barden, all right? So you just have to compare the values in the wi column, and I think the values match, so our code actually worked. Now let's complete the rest of the table, that is find the actual values and then find the errors. All right, so let's do that. That's easy. That should be easy because to add the actual value, all we have to do is write at ti here, right? So we will now see an extra column now containing the actual values, and as you can see, the actual values match also. Identical columns in the black screen and in the textbook. And the error is also easy, of course. Just what we can do is just write the expression for our error here, or we can be a little bit more formal and add another array here, E100 declared here, and just write, add an extra line in this loop, EI plus 1 is equal to yi plus 1 minus ACT of xi plus 1. But there is one problem. This loop will give us values of e starting from index 2. We do not have the index 1 here inside the loop, so we can add that manually. E1, you can understand the first point is given in an initial value problem. So there shouldn't be any error in the first point at all. So E1 should be 0. So just in the right statement, add EI here. Let's run the code and see what happens.
SRT.
Okay,
We
I
used
wrote
X rather.
X. Okay, right. Thank you. Okay, let's run the code again. Okay, we forgot to add absolute value. So ABS is another library function that gives us the absolute value of the argument. So run the code again. Now we have the error column, and I hope this matches with the error column as well in the providing the burdens book, and it does. We have just taking the last value is enough because each error contributes to the next error, right? So if the last value matched, it means that all the other values should match as well. So this is Euler's method. Now we are going to edit our code a little further to implement modified Euler method, and I will explain what that is in a moment. By the way, am I breaking anymore, or is it okay now?
No, it's clear now.
Okay, things start to happen when I share whiteboard because I think whiteboards consume more data. Okay. Okay, so in Euler method, we have seen that we say this is the actual movement of the curve from, say, this is, I'm writing a zoomed version actually. Okay, now voice is breaking. Let me try to be as slow as possible. So,
Sir, since your screencasting is all right, I think you can use Xcali draw and draw there and share the screen instead of using Zoom's board.
I can use what? Can you repeat, please? Okay.
You can screencast on your browser and use something called Xcali draw. It's the same thing, but since screen sharing is not problematic, you can do that.
Okay,
Because Zoom's whiteboard is breaking the audio.
Can you write the name of the site in text message, please? Xcali draw. Okay, thank you. I will. It's a good idea, I think. Give me a moment, please. Okay, I hope it's user friendly. Okay, I think it is. So,
Sir, are you there?
yes, I am. Give me a moment, please. Okay, I hope my voice is not breaking anymore. So, say this is the x and y exist? Okay, the first point is it's not. Okay. This website lags a bit. Everything has a negative. Anyway, it's okay. So say for example, this is our actual solution, and lot of lagging. So these two values are, of course, this is y0 and this is y1. But in Euler method, we move along the tangent line and we say that this is y1 cap. Okay. Now, there is another interesting idea that if you draw a tangent line at y1 also, and starting from y0, move along that tangent. So starting from y0, move along that tangent. So, and finally declare that this is our y1 cap. There will be still error, right? Look, what I did was I did the same thing we did in Euler method, but for now I use the slope of the wrong tangent line. Instead of using the slope of the tangent line at y0, I use the slope of the tangent line at y1, the next point. So if you use this tangent line, we would still get a wrong point, but what happens is earlier the error was positive, but now the error is negative. So this gives us another idea, and that idea is in case if we move along the straight line that is bisecting these two tangent lines, then we would end up at a point that has a lower error. So what we are suggesting is, originally we used for the ith point, we used the slope of the tangent line drawn at xi, yi. We introduced the slope of the next point that is at xi plus 1, yi plus 1. And now we are suggesting that we use neither of these two, but the average of these two. So if you use these instead of the original slope, then the drawing suggests that we will get to a point which gives us a lower error margin. So if we want to use this, the iteration equation looks like this. Y, okay, let's move to another page. How can we go to a new page? Where is the new page button here?
Sir, I think you can scroll down.
Oh, I can read it. Okay, good. So yi plus 1, original equation for Euler equation was yi plus, okay, let's write a little lower. Y I plus 1 cap is yi plus half h f of xi comma yi plus f of xi plus 1 yi plus 1. And the example of the drawing suggests that this should give a better approximation. But this method has one problem, and some of you may have already identified that we have yi plus 1 here, and yi plus 1 is the guy we are trying to find, and to find that guy we need that guy inside the expression. So this is an implicit situation, and there is a way to get rid of the situation. That is, if you know the expression for f, because you actually know the expression for f because the initial value problem is given at the beginning, right? So put that expression here. So in the expression, we would have one or multiple yi plus 1s on the right hand side. We have one yi plus 1 on the left hand side. So make yi plus 1 subject of that equation. But this is not, and there is no guarantee that we will always end up getting an implicit expression for yi plus 1, right? Because the expression for f may be complicated. It may be impossible to make yi plus 1 the subject of the equation. So this method will not work for every situation, but rather what we are going to do is, you can see that we are approximating things anyway. We are not dealing with exact things. So let's approximate yi plus 1 by using Euler's method once. Yes, something wrong here. Why? Okay. So this is the Euler's equation we have already used to solve the problem, right? So using Euler's equation, make an initial approximation yi plus 1. Use this yi plus 1 here. So use these two equations simultaneously first, and a first assumption for yi plus 1, then find the better approximation for y plus 1 using that approximated y plus 1 inside the equation. And one may be interested to write the equation in a single line like this. Some may prefer this. Y I plus 1 cap equal to yi plus half h f of xi comma yi plus f of xi plus 1 comma, instead of yi plus 1, just write the Euler equation yi plus h f of xi yi. So this will work better if you are interested in writing the entire thing in a single equation instead of breaking it into two equations. I hope the idea of modified Euler method is clear to you. If you still have any problem anywhere, please let me know. Otherwise, I'm moving on to the code. Okay, let's solve the same problem using modified Euler. So let's copy the entire code, create a new file, paste everything, and save as. Let's use Euler underscore mod because it's modified Euler. And let's name the code the same, Euler mod. So let's make the changes we need to make. All right, give me a moment, please. Let's make the necessary changes. So I think let's write it in single equation. So I am going to use a 0.5 here because equation is half h times something. And for the slope, I'm writing a bracket here. Inside the bracket, I'm going to add plus f of let's write what theoretically it should be. It should be ti plus 1, comma, y I plus 1. Theoretically, it should be this. But then again, as we have said, we cannot use yi plus 1 when we are trying to find yi plus 1. So let's replace this yi plus 1 by yi plus h times f of ti, comma, yi. Should work and should give better results than Euler method. Let's run that one. Okay, now as you can see the error column, compare it with the error column we got for Euler. All right, so we have that in the PDF. Observe this error column and observe the error column in the black screen. As you can see, the errors has been reduced significantly. So we actually needed a problem where we know the solution so that we can do these experiments and see, visualize that Euler method indeed works better than a modified Euler indeed works better than Euler method, right? So now we are ready to use both of these methods to solve problems that we don't know the solutions of, right? So we can do that, but before that, I have a question for you. Let me ask the question, but first I need to connect my graphics tab. Give me a minute, please. Okay. First of all, let me know if there is any confusion in any of the codes, or the algorithms, Euler or modified Euler. Please let me know. If there is no confusion, then please let me share that Excalibur screen again. Okay. I have a question for you. We just solved initial value problem, first order initial value problems, the general expression for which looks like this. Seriously lagging. That is why my audio doesn't break. Okay. So there is no I in the original IVP. X, Y with Y at x naught. So this is the exact structure of an IVP that we can solve using Euler method or modified Euler method. But for example, if we are given a second order differential equation that looks like this, d square y by dx square plus maybe some function a1 ax in fact, there is no problem if the function a contains y. So dy by dx plus some b xy. Analytically, it's a huge problem if the coefficient contains y, but numerically there is no problem at all. Equals to some, say, g of xy. With the initial conditions, y at x naught is the p, and y dash, since it is an initial value problem, the initial conditions should be given at the same point. And since this is a second order differential equation, okay, this was one. Since this is a second order differential equation, we must be given two expressions or two initial conditions so that we can find the value of both the arbitrary constants. Secure. Okay, my question is, can we numerically solve a differential equation that looks like this using Euler method or modified Euler method? If it can be solved by Euler method, it can be solved by it will be solvable by modified Euler as well. So let's ask the question for Euler only. Can we solve such problems using Euler's method? Can anyone answer me? Actually, there is no way we can directly solve this equation using Euler method, but there is an indirect way, very interesting indirect way. Let's see how. What we are going to do is assume dy by dx, let dy by dx equals to some function z. Then the given equation becomes what? You can understand that we are converting everything into z, all right? So d square y by dx square becomes just dz by dx. And we can replace the other things as well. But before that, I want to make dz by dx the subject. So let's write equal to here and transfer everything to the right. So we will have minus a, let's not write x comma y every time. So minus a dy by dx is simply z. Minus b, we have y here. And from the beginning, we had g on the right-hand side. So can you see that you can just write this as f1 of xy and this right-hand side as f2 of xy? So technically, we have successfully converted our second order differential equation into a system of two first order differential equations. Now, at least this is a success for us because at least we moved on to first order differential equation, which is a must for Euler method, right? Because Euler method works for first order only. And what about the initial conditions? Clearly, y at x naught equals to p is already given. Additionally, we have y prime, which is just z. So z at x naught equals to q. So we have two initial conditions and no derivatives involved. So this is the exact situation that we can solve using Euler method. Only this time we have a system instead of a single equation. Someone asked some question, I think. Gonit Joggo, did you ask any question? Okay. So, are we clear about the method using which we can convert a second order IVP into a system of first order IVP? Okay, if there is no confusion here, then this is what your offline assignment for this class is going to be. I am going to give you a second order differential equation. You have to convert it into a system of two first order equations. You have to convert the initial conditions as well. Then somehow you have to implement the Euler method. If Euler method and modified Euler method are basically same things, just one change in the expression. So let's stick to Euler method, all right? The expressions will be simpler. So you are going to use the Euler method to solve the system. So make changes in your code, necessary changes or adjustments in your code, so that your code can solve a system. You can understand that we have considered z to be dy by dx. We have two variables here, y and z. But you should understand that we are actually not interested in z. We are actually interested in finding y. Z is an intermediate variable, an auxiliary variable that helped us to convert the equation into a system of first order equations. But at the end of the day, we will get the column for z as well along with y after solving using Euler method. But we are not actually interested in the value or column of the values of z. Rather, we are going to stick with the column of y. So in your output, you have to show y only, but not z, which is dy by dx. So let me write a problem, a second order differential initial value problem. This you need
Sir,
to
how
solve.
can we find successive values of z?
How can we find successive values of z? You can see dz by dx here, right? How did you find successive values of y? in my Euler method?
We use the tangent line and found the next
Exactly.
point.
Exactly. Now we are going to use these two equations simultaneously inside the loop. Inside the loop that involved the main Euler equation, right? So we are going to use these two equations simultaneously to approximate y and z simultaneously and use them simultaneously on the right hand side expressions. Am I clear? You have the slope for z. So zi plus 1 is manageable. Using the same Euler equation, using the expression for dz by dx, you can manage zi plus 1. So you have to manage yi plus 1, zi plus 1, or evaluate yi plus 1 and zi plus 1 simultaneously. Am I clear?
Yes, sir.
Okay, this is the task. This is part of the challenge, right? So try to solve that on your own. Okay. Okay, I'm going to write a second order differential equation. The equation should be well known to you. The equation is d square x by dt square plus 25x equals to 0. And the initial conditions are x at 0 is equals to. Are you familiar with the equation? Okay, someone asked about F2. Yes, yes, it's a good point. Where is the eraser here? I think I found it. Okay. As someone mentioned, F1, F2 should be functions of X, Y, and Z. So, yes, I should have written Z here and here. Okay. Anyway, you are familiar with this equation, right? This is the equation of simple harmonic oscillation. So x is the displacement. So x at 0. Let's start from the amplitude point, the last end of the motion. So x, let's x0 be just 1, and x prime should also be given at 0 to make it an initial value problem. And we know that x prime is the velocity, and we know that velocities theoretically should be 0 at the end points. So this initial value problem represents a physical situation, and you have the solution as well, right? X of t, we can guess that using knowledge of physics. Since the amplitude x at 0 is 1, so it should be at 0, it should be cos function, and amplitude should be 1, and frequency is omega is 5 here. So cos, if I'm not mistaken, difficult to write sometimes. Cos 5t should be the expression, if I am not mistaken. Okay, so you can use this actual solution to compare your result with the actual values, and in fact also create an error column. So this is your offline assignment 2.
I have a question.
Sure.
Which H and N should we use, or we can choose anyone we want?
Which can you repeat please? Which?
H and N, like the number of iterations we need to go, and also.
Okay. Which N? Okay. Let's choose N equals to 20. And also, I have to give another point up to which you need to find the solutions. You're starting at 0, but let's, I think the interval is t from 0 to, let's say, 2. So there is going to be about 21 grid points. the subinterval length should be 0.1, right? 2 minus 0 by 2 is 0.1. So finally, the subinterval length is going to be 0.1. This is an offline assignment too. I'm going to share a Google link, Google Form link also for this assignment, and you have to upload this assignment just like the first offline assignment. Is there any question or any confusion? If there is not any, I am going to end the meeting.
Sir, is there any deadline for this assignment?
Technically, the deadline should be before mid anyway, because mid syllabus contains these topics. Mid syllabus will be the topics that we are going to cover up to this Thursday. All right. So all the topics that are going to be covered before mid are going to be included in the syllabus of the mid. So this belongs to the mid syllabus anyway, so you should practice it before mid. So technically you should submit it before mid, but for me, I generally give students time up to final exam, but it's better if you submit before mid.
So will we
Sir,
get an announcement regarding the mid syllabus?
Okay, sure, why not?
Sir, can you please provide the text or the images of the assignment on the Discord channel?
Sure, why not? I'm okay, I'm going to do that, no problem.
So we'll see you tomorrow at 9.
Yes, we will see each other tomorrow at 9. Yes. Okay, I took screenshots, so I'm going to share it with you in Discord. But Ilham was going to ask something about mid. Let's answer that first.
I guess he was asking for the mid syllables, and I think you've answered it already.
Okay, all right. I'm going
As
to
in
end.
the exact topics that we would go over, like if you would mention the exact topics so that there is no confusion.
Sure. I will mention it in Discord. All right. I'm going to mention it in Discord. All right.